Now we will be kind of shifting subjects, so if you have any questions about these rotations. Now we have kind of like, including this week, 3 weeks left. So I will be kind of jumping from chapter to chapter from now on. Now today we will be looking at the statics, elasticity, and after that, elasticity we will not be spending too much time, and after elasticity we will be starting oscillations. This is chapter 15. We will probably spend some time on Thursday and next Tuesday on oscillations, and then we will be to gravity. And the last week, if we have any time, we will be looking at fluids. So this will be the topics that we will be following. Now let's start with statics. In fact, about statics, we have already seen everything. Now when we say that something is static, it's not rotating, it's not moving, it is at rest, not rotating. So since its velocity doesn't change, it doesn't have any acceleration, so the net force acting on it is 0. The center of mass doesn't accelerate, which just means that the net force acting on the object should be always equal to 0. And then the object shouldn't be rotating. Just imagine you want to take a bridge. You wouldn't like to take a bridge that is accelerating away from you. Or you wouldn't like to take a bridge that is constantly rotating. So if it is not rotating, if the angular velocity is always 0, then the angular acceleration will be 0. If the angular acceleration is always 0, that means the net torque acting on the object is 0. So these are the two conditions that an object should satisfy if it is to be static. Now let's do some applications of this one. I'm sure you all have experienced, you have a wall, you put a stair on the wall, and it falls down. So if you just put this object over here, it just falls down. It doesn't stay there. But under certain conditions, it will stay there. So one thing you can ask is, what are these conditions? So how can we determine whether it will stand up or slide down? Now let's just make some simplifications. Let's assume, okay, this is our object. It's leaning on a wall. Let's say this angle over here is theta. Mu 0 over here is the static friction and the kinetic friction on the bottom part. So what are the forces? The first thing you have to do is always identify the forces acting on the system.
Is it instantly kinetic friction or something?
Now my question is this one. I just put it like this. And I want it to stay there the moment I remove my finger. So it will be static. I don't want it to move at all. So what are the forces acting on my system? The forces? No? There is the weight. Well, you see, since we want to calculate the torque, we also want to find at which points the forces are acting. So what are the normal forces? Okay, there is this normal force. Let's call it N1. There is one more. Yes, there is also this normal force. Let's call it N2. We don't know the magnitudes yet, so we have to find them out. Okay, now what else? There is a friction force. What is the direction of the friction force? Towards the left. So there will be also this friction force. Now, what is the magnitude of the friction force? Well, in general, yes. There will be a friction force also acting at this point. But just to simplify, to get rid of one of the forces, I assume that there is no friction force over there. And let's see if it is possible to hold this object in this orientation without a friction force over there. So what is the magnitude of this friction force? Can you say something? Somebody else? Mu s times which n? N1. Which is not. You see, it is static friction force. In general, we don't know what it is. This is the maximum value. So let's just figure out what the value of the friction force should be. So the magnitude of that friction force is less than or equal to mu s times N1. We don't, of course, at the critical point when it is about to slide, in that case it will be equal to that value, because if the friction force gets larger, if you need a friction force that is larger than mu s times N1, then it will slide. But for the general case, let's just assume that it's not sliding, it's not about to slide, so we don't know the magnitude of the friction force. Now, we have these two yes. N2 should be equal to the we will figure it out. So we have these two conditions. The total force should be 0, and the total torque should be 0. Let's start with the total force. Let's choose our coordinate axis, x and y. The total force acting on my object, let's say we will have a component in the y direction and the component in the x direction. So what is the component in the y direction? In the vertical direction? We have N1 in the plus y direction. We don't know its magnitude, but we know that it's there. There's also the weight in the y direction. It's in the downward, in the minus y direction, so it's in minus m times g. And is there any other force in the vertical direction? No. Plus the force in the x direction. Okay, we have this into the horizontal direction. And the friction force is in the minus direction, minus F friction. And the total force, since the center of mass is not accelerating, it should be 0. So if a vector is 0, all of its components have to be 0. So it basically tells me that N1 is equal to mg, N2 is equal to F friction. Now, by the way, how many unknowns do we have? We don't know N1, we don't know N2, we don't know the friction force. So we have 3 unknowns. Well, we already have found one of the unknowns. So we have 2 unknowns left. So this is one equation relating these 2 unknowns. So we have to find at least one more equation relating our unknowns. And that would be from the fact that the torque, the total torque acting on the system should be 0. Now let's calculate the torque. So if you want to calculate the torque, first you have to choose some reference point. With respect to which point would you like to calculate the torque? The bottom point, fine. Okay, let's go with the bottom point. Is it rotating with respect to any point? So whichever point you choose, it should be 0, the total. Your friend wanted to use the bottom point. So let's give some more numbers. Let's say that the total length is L. Now the total torque relative to, let's say, this point A is equal to, let's say, the Z direction is also towards U. Now the torque, all the torques created by these forces will always be in the Z direction. So let's calculate the torques created by these different forces. The friction force, what will be the direction of the torque created by this friction force? 0. The friction force is acting right at the point A, so it doesn't create any torque. What about N1? It's also 0. So we have the weight. What is the direction of the torque created by the weight? So this is the position at which the weight is acting. This is the direction of the weight vector. So it's out of the screen. It's in the plus Z direction. And the magnitude? Well, the magnitude of the weight is mg. The distance it is acting is L/2. And then we need to find the sine of the angle between the two. So this is R. So this angle over here. You see, this is R of the weight. This is the weight. The angle between the two is this angle over there, which is pi/2 plus theta. This is the torque created by the weight. Now let's look at the torque created by N2. What is the direction of this torque? This is the position vector. This is the point at which the force is acting. This is the N2, the force. So if you imagine rotating this position vector towards N2, so this is the direction of the torque into the screen, in the minus Z direction. So it's minus its magnitude, the product of the magnitude, the product of the force times the force, the magnitude of the force times the magnitude of the point, the distance of the point at which the force is acting, times sine of the angle between the two. It is this angle over here. So that angle is pi/2 minus theta, pi minus theta. You see, this angle over here is theta. So this is the torque. Let us simplify it a bit. This is mg L/2 cosine theta minus N2L sine theta. And since my object is not rotating, that point is fixed. It is not rotating around that point. It's not. It doesn't have zero. It has zero angular acceleration around that point. So this torque should be 0. And that tells me that N2L sine theta should be equal to mg L/2 cosine theta. If we cancel the L's, N2 is equal to mg/2 cosine theta over sine theta. So we already determined another unknown. We didn't know N1. Well, from the total force equal to 0, we had already determined N1, it should be mg. Here we had a relation between the unknown friction force and the N2. And now from this torque equation, we had determined N2 because everything else we already know. Since we know N2, we already know that this is equal to the friction force. This is equal to N2, which is this one. Now we already know that this is static friction force. So if the object is to stay there this force has to be less than or equal to mu s times n1. And we had already determined what n1 was. This is mu s times mg. Or tangent theta should be larger than mg over 2 mu s mg 1 over 2 mu s, larger than or equal to. So this condition should be satisfied. So let's see, does it make sense? Now, if the friction force is very large, if mu s is very large, so you have a surface that's really rough. So from everyday experience, we know that even for small angles, let's say the surface of this one is rough. So even for very small angles, it will more or less stay. So even for small values of theta. You see, if the friction force is large, that means this mu s is large. So this number is small, so tangent theta can take small values. Well, if tangent theta gets smaller values, that means the angle theta itself can take very small values. Now, another limit that we can look at is if the surface is very smooth, if mu s is very small. This relation tells me that if mu s is very small, then this number over here is very large. It's huge. So tangent theta should be very large. And remember the properties of tangent. For 90 degrees, tangent theta is infinite. So if mu s is very small, it is a number very close to 0, then theta should be very close to 90 degrees. So this is, here the surface is quite smooth, the friction force is very small, so even for such an angle, it doesn't stay. It slides. So if the angle is close to 90 degrees, only in that case, it will stay. So here you see that there's another way of measuring mu s. If you can create such a system, and if you can determine what this angle theta is, you know what mu s is. What is the critical value of this angle theta? That tells you what mu s is. Now, any questions on this one? Now, let's do one more example on statics, and we will just pass with the statics. So it's just an application of what we already know. Before, we were calculating the angular acceleration and the linear acceleration, and now we know what their values are. Their values are 0, and we are trying to determine the conditions on the unknown forces. Now, another exercise is bridges. So suppose you want to build a bridge, and of course when you are building your bridge, you would like your materials to be strong enough to be able to carry the weight. And do you remember the example where I had brought an oklava, this long stick, and we could determine the center of mass? In fact, you can just imagine that these two things are my fingers. And so, if you move this one, how could I determine the center of mass in all the cases? Now, of course, when I'm moving my fingers, the thing that determines whether the finger and this stick is sliding with respect to each other or not would be the friction force. If the friction force between my finger and the stick is large enough, then the stick will move. If it is not large enough, then my finger will slide and the stick will stay where it is. And so then the friction force is basically related with what are the normal forces acting on these two endpoints. So let's just imagine that this is my center of mass. It is at a distance x from one end and y from the other end. The whole thing has a mass m. Now, what are the forces? there is a weight acting on the center of mass, and the two normal forces, N1 and N2. Well, let's just assume that my fingers are fixed. So there's no friction force. The total force, let's say again, the x-axis, the y-axis, and the z-axis. What is the total force acting on my system? There's only the y component, all the forces are vertical. So what are the total force in the y direction? N1 plus N2 plus N2 minus mg. So I have these two unknowns, N1 and N2, and this is one of the equations relating N1 and N2. Now let's calculate the total torque. Again, this is in the z direction. Okay, the torque with respect to which point? Center of mass. Okay, that's a possible choice. So what is the direction of the torque created by N1? You see, we are calculating the torque with respect to the center of mass. And the torque created by N1 relative to the center of mass. N1 is this one. R N1, if you just rotate R towards N1, this is in the minus z direction. It's minus N1 times X times, what's the angle between the two? Sine of 90 is 1. So this is the torque created by N1. Now what about N2? Okay, this is the direction of the force, of the point. This is the point where the force is acting. This is the direction of the force. If you just rotate it, right hand is towards you, which is the plus z direction. Plus N2 times y. This should also be 0. So this gives us another equation. N1 times x is equal to N2 times y. In fact, to explain how that stick example works to find the center of mass, this is enough. What does this tell me? If N1 gets closer to the center of mass, so x gets smaller, in that case, N2, y has some value. If x gets smaller, N2 should get smaller, and N1 gets larger. So if my N1, if left point comes close to the center of mass, then the normal force exerted by the other finger gets very small. If the normal force is small, the friction force between the stick and my finger is very small, whereas the friction force between this finger and the stick is large because the normal force here is large. So there is no friction force over here, so this finger just slides relatively easily until it gets close to the center of mass. When this finger gets close to the center of mass, then there's a larger normal force on this finger than on this finger. So there's a larger friction force here than on the other one. So if the friction force on this one gets small, it will just slide. If it slides until it gets closer to the center of mass, and this works until both fingers come very close to the center of mass. That is why when you take the stick, put it on your fingers, unless it gets stuck somewhere, if you move your fingers close to each other, they will join right at the point of the center of mass. Now, in this one, let's solve this example. So we have that this is N1x is equal to N2y. So let's just say N1, we have these two equations. this one, and the other one, so from here we can just say that n1 is equal to n2 times y over x. So this one tells me that n2 times y over x plus 1 is equal to mg. n2 is equal to x over x plus y times mg, and n1 is equal to y over x plus y times mg. So if you just do the algebra, this will be the n1 and n2 that you obtain. Now we had made an arbitrary choice to start the solution. Now when we were talking about the torque equation, we said let's choose a point, and one of you just proposed to choose the center of mass. You don't have to choose the point center of mass. Let's see what happens if we choose another point. Let's say we can prefer to calculate the torque relative to this point. Let's say the point A. Now the torque relative to the point A, which should also be 0 by the way. Again, the torque will be in the z direction. Okay, what is the torque created by N1? It is 0. It is acting right at the point A. What is the torque created by the weight? Direction of it? You see, this is the position of the, okay, yes, this is the position of the, let's say that I'm the point A. This is the position of the center of mass. This is the direction of the force. So if you just imagine rotating the position towards the force, right-hand rule is into the screen. So it's in the minus z direction. Minus x times mg. Now what is the torque created by N2? Its direction is plus that. This is the position at which the force is acting. This is the direction of the force. So it's in the plus z direction. Plus N2 times x plus y. And this should be 0. Now if this is 0, this tells me that N2 should be equal to x over x plus y times mg. Just as we had found beforehand. Now this choice of the point relative to which to calculate the torque doesn't really matter. Eventually you get the same equation and the same solution. It's just up to you. But of course, if you chose this, we had chosen this point beforehand, we could have obtained N2 directly. In the other, since we chose this point initially, we had to take a few more steps to obtain the final result. The final result is always the same. So whichever point you choose to calculate the torque, you always get the same result. Any questions? I'm only asking you for the directions. So you have to specify two directions. One, the direction of the torque created by the string, the tension of the string. The other one is the direction of the torque created by the weight of this rod. With respect to this point. Only the directions, not the magnitudes or anything else. You should discuss your solutions outside.
Altıncı quiz galiba.
Quiz devam ediyor.
6 yaptı ama quiz şey var.
You should discuss outside. Sohbetinize dışarıda devam edebilirsiniz. Quiz hala devam ediyor. Your last minute on the quiz.
Direkt yürüyor muyuz?
Quiz devam ediyor. So your time is up. Quizini getirmeyen varsa.
Reportların sonuncusu 12.si yine hocam 0 gelmiş.
Bakalım. Orada şeylere baktın mı?
Açıklaması
Komentlerine.